We're jumping into a topic called the binomial theorem, which you probably have seen in Algebra 2 as far as how to expand a binomial raised to a higher power, like the fourth power, fifth power, even up to like 10th or 11th power. So this information will come from section 9.2 in your textbooks. So our goal for today, we're going to focus on using Pascal's triangle with the binomial theorem to expand these binomials. There is another way for generating the coefficients using something called a combination, but the county seems to have cut that out from the topic this year. So instead of trying to show you both methods of generating the coefficients, we're just going to focus on using Pascal's triangle. So I know that this formula looks hideous, but the idea here is that when you have something like x plus 3 raised to the 6th power, I'm going to show you guys a way to quickly expand all of that without sitting there and distributing it over and over and over again, x plus 3 times x plus 3 times x plus 3 times x plus 3 times x plus 3, because that takes a very long time. So there are three pieces to each term. There's the p piece, which is the coefficients, and we're going to find that using something called Pascal's triangle, which I'll show you in the next slide. Then there is the exponent for a, so whatever's in the first spot of the binomial, it starts to the nth power. So whatever you have for the exponent on the outside, it's a to that power, and then it slowly decreases. So you have a to the nth, so let's pretend it's the 6th power for a second, a to the 6th power, a to the 5th power, a to the 4th power, and you keep going until eventually you hit a to the 0 power. And then the last piece of each term is b being raised to a power. B is the second number in the binomial. Now it's going to start from the 0 power and it's going to slowly count up until it hits whatever the exponent on the outside is. So it starts with b to the 0 power, b to the 1st power, b to the 2nd power, and it keeps going all the way up until you hit whatever that power is outside of the parentheses. So basically you have the three pieces, the piece from the triangle, a exponent counting down, and the b exponent counting up. And you just go through that pattern for each term until you're done. So first let's talk about Pascal's triangle. The idea is for when you have something like a plus b to the 1st power, so this is what we call the first row because it's the 1st power on the outside of the parentheses, your coefficients are 1 and 1. Now, the way we generate this triangle is by putting 1s down the outsides of the triangle, and then whenever you have a pair of numbers, like here I have a 1 next to a 1, if you add those up, you put that answer underneath in between in the next row. So 1 plus 1 is 2. And then if you look here, I have a 1 and a 2 next to each other. If I add those up, 1 plus 2 equals 3, I put that in between in the next row. Same thing on this side. I have a 2 and a 1. I'm using this 2 again. You can reuse numbers. So 2 plus 1 is 3, and I put that in the next row. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. So let me show you that I'm going to add another row here. What if I was dealing with a plus b to the 5th power? Well, I would still have 1s on the outsides, and then 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, and 4 plus 1 is 5. So those would be the coefficients of the next term. So I would have 1, 5, 10, 10, 5, and 1. And then the other piece, I talked before about how a's exponent is going to count down. So if you're doing a plus b to the 3rd power, it starts off with a to the 3rd, and then a to the 2nd, a to the 1st, a to the 0, which you can leave off. B counts up. So b to the 0, which you leave off, b to the 1st, b to the 2nd, b to the 3rd. So I'm going to do the same thing here. I'm going to start off with a to the 5th. So the first term has a to the 5th power, and then it would be a to the 4th, a to the 3rd, a to the 2nd, and a to the 1st. So I'll just write a. And then b is the one that counts up. So you're not going to have it in the first term because that's b to the 0. So that one's done. The next term would be b to the 1st, and then b to the 2nd, and then b to the 3rd, b to the 4th, and finally b to the 5th. So that's how you create a row of this. So you guys may have to create more rows in some of your classwork assignment. You may have to go to the 6th row or the 7th row. So make sure you understand how you put 1s down the outside of the triangle, and then whenever you have a pair of numbers, you add them up and put the sum underneath in the next row. So here's a quick example of what you'll see on the first, actually most of the assignment that you'll be doing, numbers 1 through 7 of the assignment. So I need to use Pascal's triangle, and specifically I'm going to be using the fourth row. Now you don't have to rewrite the triangle for every single example. It doesn't change from question to question. So let's start off by looking at what we have for the fourth row. So the fourth row has the coefficients 1, 4, 6, 4, 1. So I'm just going to write out 1, 4, 6, 4, 1. And then in this case, my a value is x. The first thing in the binomial is x, and it's going to be raised to the fourth power. So I'm going to start off with x to the fourth and count down. So just subtract 1 from the exponent over and over again, and then you don't have to write x to the 0. You can just leave that off because anything to the 0 power equals 1. Okay, and then the b term, which in this case, the second thing in the binomial is a 2, this one slowly counts up for the exponent. So it starts off at 0, so I don't write anything in the first spot, and then it's 2 to the first, 2 to the second, 2 to the third, and 2 to the fourth. I put a little dot in there just to indicate I didn't want to confuse myself and think that was 12 raised to the fourth power. It's 1 times 2 to the fourth power. Now each of these terms should be separated by a plus sign, and then I should be able to actually evaluate this a little bit. Instead of writing 1x to the fourth, that's just x to the fourth power. But on the next one, I have 4 times 2. So I have 4 times 2, which is 8 x to the third power. In the next one, I have 2 squared, which is 4. And I'm going to multiply that by the 6. These are in the same term. So 4 times 6, and that's x squared. Next one, I have 2 to the third power. That's equal to 8. And then 8 times 4, these are in the same term, equals 32. And the last one, you can ignore the 1. 1's not going to change anything. But I do have to evaluate 2 to the fourth power, which is equal to 16. So there is my expanded polynomial. Now the reason we do this is because it's a lot easier than writing x plus 2 times x plus 2 times x plus 2 times x plus 2 and then sitting there and foiling it out over and over and over and over again. It takes a long time to get the answer, and you have to do a lot more adding and multiplying than we did in our example. Okay, here's another example. This one's a little bit trickier because I have a variable in both spots, but it's actually going to be very similar. So first, let's look at Pascal's triangle again. I'm using the a plus b to the fourth power, so it's going to be those same coefficients, 1, 4, 6, 4, 1. So I just like to leave a good amount of space between each term, 1, 4, 6, 4, 1. And then you start off, in this case it's 2x, so you might want to use parentheses here, so this will be 2x to the fourth, and then 2x to the third, 2x to the second, and 2x to the first. And then the other way around, b is going to count up. So 3y to the 0, which I'm just leaving off, and then 3y to the first, and then 3y to the second, 3y to the third, and finally 3y to the fourth. So setting up the expression was pretty similar, but I do have more computing I have to do. Don't forget that the property for having something in parentheses raised to a power, when you have a term like this, you need to apply the exponent to all of the bases. So this is actually 2 to the fourth power, which is equal to 16, and x to the fourth power. But then that stuff was being multiplied by a 1, so I don't have to do anything else there. So 2 to the fourth power is 16, x to the fourth power is x to the fourth. Next, I'm going to have, let's do this in stages. So I'm going to do 4 times 3, which equals 12. And then I have 2 to the third power, which is equal to 8, and x to the third power times y. So I'm just trying not to do too many of the multiplications at once. So I did the 4 times 3, which were on the outside to get 12, and then I went ahead and applied the exponent to the inside. Let's do the same thing for this next one. So I'm going to have 6, and then this is going to be a 4, and this is going to be a 9 because I'm taking that exponent of 2 and I'm putting it to all the bases inside parentheses. So I'm going to have 6 times 4 times 9, and that's going to be x squared and y squared. Then I'm going to have 4 times 2 times, this last piece is going to be 3 to the third power, which is equal to 27. And then that'll be x to the first, y to the third. And then the last piece, 3 raised to the fourth power, is going to equal 81. So I still have more combining I need to do here, because, for example, I need to be able to multiply 12 times 8. First one's done. 12 times 8 is going to equal 96, and then that's x to the third power, y to the first. For the next piece, we have 6 times 4, which is 24, and then we are multiplying that by 9, so we should get 216 x squared, y squared. And then 4 times 2 is 8, so 8 times 27 is also equal to 216. And the last piece is already done, 81y to the fourth. So there is our expanded polynomial. So it just takes a little bit more work when you have numbers and variables in both of those spots, but the process is generally the same. The last type of question you'll see on the assignment, they might not ask you to expand the entire expression, they might just want to see one specific term. So in this case, they're only asking us for the x to the fourth term. Now, I do have a binomial being raised to the sixth power, so I'm actually going to have to expand my Pascal's triangle a little bit. So we're going to look back at that in just a moment. But we're not going to do all of the terms. We're just going to focus on the one that we think would end with x to the fourth power. So if I have x minus 2 to the sixth power, let's go back to the triangle. The next row of my triangle would be the sixth row, and that would be 1, 6, 15, 20, 15, 6, and 1. And then think about your exponents for a second. It would start off with a to the sixth, and then it would go to a to the fifth, and then it would go to a to the fourth. So what I'm actually going to be looking for in this last example is this third term in the sixth row. So actually I can just kind of skip the other stuff. I know it'll be a to the fourth, and then I also know that the b piece, it's going to start off b to the 0, b to the first, b to the second. So I need to find the third coefficient, which is 15, a to the fourth, b to the second. 15, a to the fourth, b to the second. Okay, now in this specific example, my a value is an x, so it's going to be x to the fourth power, and my b term is going to be -2, but it's being squared. So if I evaluate this, -2 squared is 4, and then the 4 times 15 is equal to 60, x to the fourth power. So we didn't have to go through a whole bunch of work if we're only interested in the one specific term. So just think about which a and b powers you will have and use the coefficients of the row and figure out what the powers on a and b should be according to the information they've given you. That was the x to the fourth term. We ended up with x to the fourth power for our answer. So there's more of the polynomial, we just aren't going through the effort of finding it. So thank you, that should be all for the notes today.